Good afternoon, everybody. I'm Amandeep Sharma, pursuing my PhD in Electrical Engineering Department in NITTTR Chandigarh. I'm working on condition monitoring of electrical machines, and basically my job is to have a system designed for automated diagnosis of electrical machines. These are the contents of the presentation. I will talk about motor faults and in general the methods to diagnose the faults. Then motor fault diagnosis using LabVIEW will be discussed a little bit. Then the experimental setup which can be used for fault diagnosis will be discussed. Then some results and discussions which are to be made in this context will be discussed. Then data analysis and results for ABB motors, and then I will give some references. As you all know that induction motors or simply motors are the backbone of modern industry. They are used as prime movers. That is, if you want any kind of mechanism like pumps, compressors, blowers, fans, etc., those are all running on motors, and specifically induction motors are widely used because of their good features like reliability, robustness, low cost, less maintenance required, etc. However, being rugged, these motors also may fail because of some unforeseen reasons, which may cause costly repairs and even total machine replacement sometimes. And therefore, it is required that these machines should be diagnosed for faults at an early stage so that we can accordingly plan our maintenance operations, and we can also have some sideways arrangement of these motors. So these are some of the common machine related problems. As you know, in industries, there are conveyor belts, gearboxes, etc., which are used to drive the kinematic tool chain ahead of the motor. Motor being driving the whole machinery, but these mechanical parts are also subject to worn or wear by time. And looseness is also one of the common machine related problem. This is usually caused by improper manufacturing or improper installation of the machines. Then we have misalignment. Misalignment is also a big cause of machine related problems. If you have misalignment, then your bearings may fail earlier than the expected time. So all these problems may cause earlier machine failures, and therefore we are supposed to have some diagnosis system which is able to predict the fault at a very early stage so that we can have maintenance activities being performed on the motors and the machinery so that an abrupt failure is avoided. These are the trends in maintenance strategies which are developed from past to present. First of all, maintenance in earlier days was failure oriented. That means whenever a fault occurs, then the machine was replaced or the maintenance was carried out. Then the preventive maintenance followed. In this, we have a time-based maintenance. That means after every 3 months or after every some stipulated time, we have to carry out the maintenance of the machine. And then the condition monitoring has evolved. In this kind of strategy, we have the condition of the motor being continuously monitored through some sensors like vibration, current sensors, flux sensors, acoustic sensors, so that we can have a pre-glimpse of what is the condition or what is the health of the motor that is being run in the industry. And lastly, we have the predictive maintenance. Predictive maintenance means we are going to predict when the maintenance activity is to be carried out. That means if in the next 6 months, the maintenance is required or not, that has to be predicted using some maintenance techniques, condition monitoring techniques. Condition monitoring is basically what it is referred to as the process of monitoring the specific parameters of motors like vibration, voltage, current, temperature, or acoustic noise, so that we can forecast the need of maintenance before the failure of the or damage of the machine. So basically it is a health diagnosis system. As you know, in humans we have ECG, EEG and EMG being carried out. These are the signals which are coming out of our body. These signals can be used to diagnose our health. So similarly, in motors we have these signals which can be picked up through sensors and then which can be used for fault diagnosis of the motors. Okay, so this is the basic glimpse of condition monitoring. This is the picture showing the constructional details of an induction motor. As you know, induction motor is the widely used motor in the industry. It is approximately 95% of the cases that induction motor is used nowadays. It is superior to other motors because it is low cost and requiring very less maintenance, and it has various parts like stator, rotor, then bearings, then it has a stator winding. All these parts are there in an induction motor. So any of these parts may fail over time and which may cause the failure of a motor. So we have to diagnose the failure at an early stage so that the complete shutdown of the plant is avoided. Basically, motor faults can be classified into two parts. One is mechanical faults and other is electrical faults. Electrical faults include stator related faults and rotor related faults, whereas mechanical faults are bearing, gearbox faults or torque oscillation, and air gap eccentricity is also a kind of mechanical fault. So in mechanical faults we have bearing faults. These can be further classified as inner raceway fault, outer raceway fault, and those caused by rolling elements. Here you can see that there are two rings. One is outer ring and other is inner ring, and there are some balls inside. So any of these three components may fail earlier than time, and so it may cause a premature failure of the machine. Similarly, we have centricity fault. The centricity fault is of two types. One is static centricity, other is dynamic eccentricity. These are basically special cases of bearing misalignments or manufacturing misalignments. In case of eccentricity fault, we have the rotation of rotor axis being displaced by a constant distance from the actual center of the stator. So here you can see that when the rotor is rotating in the stator, it is having an uneven air gap in between. So this uneven air gap is causing unbalanced magnetic pull, and which is a cause of earlier machine failure. Then we have electrical faults. In this we have lamination or frame faults and winding faults. Winding faults are caused by shorted turns. As you can see in the diagram, there are windings in the stator of the motor. If these windings got short circuited, then we have stator interturn shorts. So These can be phase to phase, phase to coil, or coil to ground, etc. And similarly, we have rotor faults. Rotor faults are basically broken rotor bars and broken end rings. These are the various statistical percentage of occurrence of induction motor faults. As you can see that bearing and stator faults are the most prevalent faults. These are approximately 70 to 80% of the faults which are occurring in induction motor. Then we have rotor faults as the third largest cause of failures. These are various motor faults as we have discussed. Power quality is also one of the problems in induction motors. Now we come to fault diagnosis methods. As we can see that there are various signals which are associated with the motor. We can diagnose any of them, or commonly we are using vibration, temperature, and acoustic measurements to carry out fault diagnosis. Whenever a motor is failing in a particular time instant, then it will cause some change in the characteristic signals, like vibration may increase, the motor may get heated up very early, and it may cause very peculiar noise, acoustic noise in the environment. So all these signs can be measured and can be fed to a diagnosis system so that we can have a early detection of motor failure. Basically, vibration monitoring and motor current signature analysis are nowadays very highly used because these are easy to acquire from the motor and are giving very high indication of the motor failures. Now we come to motor current signature analysis. Basically, it is a technique which is used widely for diagnosis of induction motor faults. Researchers have revealed that motor currents and voltages are always modulated by the fault condition inside the motor. That means whenever a motor is running, so if it is unsymmetric, a motor is basically designed in a symmetric way, but if it is having some fault, then unsymmetry may occur in the motor. This unsymmetry or asymmetry will cause a imbalance in the current or voltages of the motor. So these can be diagnosed for fault. The spectrum analysis of motors current and voltage can be detected using various faults present in the motor without disturbing its operation. That means we can online diagnose the fault of the motor. So motor current signature analysis is commonly used technique. It is based on spectral component analysis of the stator current. So in this diagram you can see basically what we are doing. We are acquiring the current being fed to the motor through a current transformer. This signal is fed to a signal conditioner. That means we are amplifying the signal because the output of current transformer is very low. So we are here filtering and amplifying the signal. Then in the next stage it is fed to a spectrum analyzer. Spectrum analyzer basically computes the FFT or the frequency domain characteristics of the signal. And by observing the frequency domain signal characteristics, we can have a idea of the fault which is going to occur in the motor. So this is the process of inducing current components in the stator. The idea behind this diagnosis is that whenever the motor is running, any fault occurring in the bearing or rotor will cause some stator vibrations. These vibrations will affect the flux of the motor. Okay. So flux will be affected. These disturbance will affect the rotor vibration. It will cause rotor vibrations, which will affect the modulating magnetic field, and then current components are induced in the stator, which will appear in the spectrum of the current. So by observing the spectrum of current, we can diagnose the fault of motor. What are the various advantages of electrical signature analysis? Basically, it is easier, simpler, and cheaper to measure. We can measure the signal online. That means the motor is running and we do not require any shutdown of motor, as in the earlier maintenance strategies. We are supposed to shut down the motor and then diagnose the fault. But in this case, the online fault diagnosis is possible. Measurement of signals from supply control panels can be made. And this is a very easy technique, and it can diagnose the fault from motors which are placed in remote and inaccessible and hazardous areas, like underwater motors or motors working in chemical plants can be easily diagnosed. So this is the methodology. Here, the current of the motor is monitored. It is the signal conditioning is applied, and the preprocessor is basically extracting some features of the current signal, like fast Fourier transform, average, RMS, kurtosis. Any statistical parameters or frequency domain parameters can be calculated here. Then some algorithm is applied, which will generate some feature vector or some classification, and then the exact classification or the indication of motor fault is obtained from diagnostic and classification processor. So this is the basic methodology which is adopted in motor current signature analysis. Here we can see that there are various types of faults in the motor which can be diagnosed by using various types of signals like vibration, current, magnetic flux, voltage, acoustic signals, etc. These are fed to the signal processing device, which will compute the RMS, Fourier transform, time frequency features, wavelet diagnosis can be done, Parkes vector approach can be used. All these will generate some features or some indicators which will be given to the fault detection fault detector, which will have model based or fuzzy or neural network based diagnosis of faults. This will be done by using expert knowledge base. That means we are having some theoretical knowledge of the fault occurrence. This will be utilized here, and we can diagnose the fault of motor. This is the basic experimental setup which we have used. We have used a 3-phase induction motor. The voltage and current which is being fed to the motor are acquired using a data acquisition system. An accelerometer is also used for measuring the vibration signals from the motor's body. And all these signals are fed to the computer for further analysis. The load on the motor is a very important factor because the signals which are acquired are having a very high correlation with the loading effect. If the motor is highly loaded, the features of the motor will altogether be different than when the motor is at no load. Okay, so this is the basic setup for online condition monitoring. So here we have used these resources. This is our experimental setup. Here we have an induction motor which is being loaded by this pony brake arrangement. Here we have placed two accelerometers on the X and Y axis of the induction motor for acquiring the vibration signals from the motor. Then we have this loading arrangement which can be used to load the motor. And then we have a data acquisition system which is CDAC provided by NI National Instruments. We have a current transformer here. The signals from this motor are fed to the computer which can be further analyzed using various algorithms. So in hardware we have NI9178. This is an 8-slot DAC chassis which is used for data acquisition. Then we have add-on cards here. One is 9244. This is used for voltage acquisition. It can measure up to 400 volt RMS line to neutral and 800 VRMS from line to line connections. Then we have 9227. This is a current input module. It can acquire up to 5 amperes of current. Then we have 9234. This is a 4-channel dynamic signal acquisition module. It can be connected to accelerometers or acoustic sensors like microphones for acquiring the motor's data. Then we have industrial accelerometer and cable. As you can see in this diagram, we have placed 2 accelerometers in the X and Y axis. And the softwares which are used here are LabVIEW and MATLAB for analysis. This is another picture for the same experimental setup. We have also used this variable frequency drive for controlling the speed of motor. And here we are having this motor with inter-turn short circuit facility. I will discuss about this motor in the next slides. These are the hardware components that are used. This is the 9234 for measurement of vibration, 9227 for measurement of current, and this is 9178 8-slot CDAC chassis. So these are C-series modules provided by NI which can be mounted in this chassis for acquisition of signals. In the software part, we have front panel and block diagram. In LabVIEW, we code the program by using graphical coding. It is slightly different from conventional text-based programming. Here we have to just put some blocks and connect them using wires. And when we run this code, then we will have some signals being acquired from the motor. So this is the front panel. Here you can see that these are the current signals being acquired. This is the voltage signal, and these are the vibration signals from the 2 axes of the motor. And this has facility for the acquisition of the signals. That means we can save or store the signals for analysis at a later time. So first of all, we will discuss about this motor that we have developed. We have rewound this motor. This is a 0.5 HP 3-phase induction motor. We have got it rewound, and we have made provision for creating some inter-turn short circuits in this motor. As you can see, it has 3 phases. Each phase has 4 coils, and each coil has 147 turns. So we have made some special tappings out of this phase, and here we can short these turns so that we can create artificially an inter-turn short circuit fault in the motor. After creating this fault, we will acquire the signal from the motor terminals, and then we will be able to diagnose the inter-turn short circuit fault. So here As you can see, in this case, first of all, we will acquire the data of the motor without any turn short. That means the motor is in the healthy condition, and then again in the faulty state we will short some circuit, short some turns of the motor, and then again acquire the data from this motor, and then we will compare the two and have some classification of the motor signals for fault. So for bearing faults, we have artificially created some holes in the inner and outer race of the bearings. As you can see here, we have artificially created a small hole in the outer race of the bearing. The size of this hole is 2 mm. For further analysis, we have also created a fault here for 4 mm. That means we are increasing the severity of the fault. And similarly for inner race, we have also created 2 and 4 mm dia faults. And also we have created multiple faults in the outer race. So the data of the motor is acquired both for healthy bearing and faulty bearing, and the signals are diagnosed further. For diagnosis of rotor faults, we have put hole in the bars of the motor. That means we have artificially created broken rotor bar fault. First of all, we have created only a single broken rotor bar fault. Then we have gone for 2 broken rotor bars, then 3 broken rotor bars. So in all the cases, we have acquired the data for motor under different loading conditions. So by varying the load and varying the severity of the fault, we have acquired various data, and these data are further analyzed using LabVIEW and MATLAB for the classification. So these are some of the important expressions and formulas. Those are relating to induction motor. We have NS, that is synchronous speed of the motor, given by 120 F by P, where P is the number of poles, F1 is the supply frequency, and slip is given by this formula, where NR is the rotor speed. So for detection of broken rotor bar fault using MCSA, we have some formulas like this. So whenever we will have we will do FFT of the motor's current, then we will have some peaks like this. For a healthy motor, we will have only a fundamental F1 peak here, but for case of broken rotor bar fault, we will have 2 extra peaks. These are called as twice slip frequency sidebands, and these are caused by broken rotor bar faults. Okay, so whenever there is a fault in the rotor of motor, so there will be some extra peaks in the spectrum of motor current. So this is the formula for this. We have 2 sidebands occurring in the current spectrum of motor because of fault in the rotor. As the severity of this fault is increasing, we have seen that the amplitude of these peaks is increasing. That means the difference between the fundamental and these peaks are becoming less. So this is an indicator of the fault severity and the presence of broken rotor bar fault. So similarly, we have formulas for different other faults. For stator faults, we have these frequency components which are observed. For air gap eccentricity, we have these kind of frequency components being observed. And for bearing faults, we have these type of fault frequencies which are occurring in the current spectrum. So we have discussed about motor current signature analysis. Motor current signature analysis basically is the procedure for acquisition of current from the motor terminals, and then the FFT of the motor current is done so that we can observe some characteristic peaks. And if we observe these frequency components in the current spectrum, then we can say that there is some fault in the motor. However, there are some shortcomings of this method. One is that if we have a pulsating load, that means the load is not non-stationary, then the current of the motor will be varying over the time period. So it will produce some non-stationary signals in the motor current, and we will have no sharp peaks like this. We will have a very blurred spectrum of the motor. So in that case, we have to apply some time frequency transformations like STFT, wavelet, etc., so that we can process the signal. Okay. So that is what is the main motive of ABB for giving this project to us. So they have their own condition monitoring solutions. They are providing condition monitoring solutions worldwide to other companies like various oil mills or various hydroelectric power stations. They have a vast set of algorithms for fault diagnosis of motor. However, they are interested in non-stationary signal analysis. That means the case where there is some load pulsation or the variation is there in the voltage of motor. So in that case, this MCSA method fails. So we have to apply some newer techniques so that we can classify the motor's fault. One of the method is the discrete wavelet transform. So this is a time frequency based method. Here the acquired signal is passed through a low pass and high pass filter, and we are getting some detailed and approximation coefficients here. Basically what is done, the signal is passed through a high pass filter and then resampled, so that we are getting the high frequency components of the signal. Similarly, we are passing the signal through a low pass filter so that we are getting the approximate coefficients of the signal. So this is done again and again so that we can decompose the signal into various components. So in wavelet, we can decompose the signal just like in FFT. FFT is basically decomposing the signal into sum of sines and cosines. So in wavelet, what we are doing, we are disintegrating the signal into various frequency bands here by using various filters. Low pass and high pass filter, again this will be passed through the low pass and high pass filter again. So we are basically decomposing the signal into various frequency bands, and the frequency band of our interest will be then used for computation of the FFT, or will be analyzed for statistical parameter calculation. So this is done to basically denoise the signal or to demodulate the signal. So wavelet, discrete wavelet transformation is a technique for analysis of signals. Then we have another approach that is called as Parkes vector approach. In this case, the three-phase current of the motor is transformed into two-phase system. That is, we are now calculating the quadrature and direct axis of the current, and these are used to further form a Parkes vector circle. Here you can see that if these two currents are plotted against each other, then we will have a circle here. For a healthy motor, we will have a perfect circle, but for a faulty motor, we will have the shape of circle being distorted, or there will be some features of the fault occurring in the locus of the circle. For this, we have just designed a simple VI in LabVIEW. This is the block diagram. This is the front panel of the VI. By analyzing the motor currents from ABB, we have seen that the Parkes vector circle is just showing some features of some high frequency content in the current. So these may be caused by some load pulsation or by some fault. So we have to basically separate whether it is being caused by some load pulsation or by occurrence of some fault. Now this is another motor. In this case, we are having a perfect circle. So that means the motor is healthier than the earlier one. In this case, we have the locus being drawn like this. So there is some fault or some load pulsation in the motor. So these data points can be fed to some further classifier like neural network, fuzzy logic, etc. for exact for machine learning application, so that we can find the exact fault in the motor. This is another example. Here we have used the interturn short circuit analysis. We have done the interturn short circuit analysis, that is the interturn fault in the motor, by using the simple virtual instrumentation based program. This is the flow chart for this. We have acquired the current from the motor, 3-phase current. Then we have done the DQ transformation, that is we have converted the 3-phase to 2-phase system. Then we have used the Parkes vector analysis, and then we have done the analysis of the pattern Parkes current vector. So for a healthy motor, we can see we have a perfect circle, but in case of faulty motor, in this case we have 2.2% of the turns being shorted in one phase. And as we apply the loading, this is for no load, this is for half load, and this is for heavy load. So we can see that the deformation of the circle is occurring for heavy load and for high percentage of shorted turns. So here we can define some fault severity index for diagnosis of the fault. These are some of the results being obtained from this experimentation. Then we come for the model-based fault diagnosis. Model-based fault diagnosis have some advantages over conventional diagnosis. Here we have the advantage that we are not supposed to measure the actual parameters of the motor under test. We are just supposed to have the healthy motors data and the faulty motors data, and we can model the signal or model the motor, and then we can have some feature extraction being done by subtracting the actual signal from the motor and the signal from process model or signal model. And these features are being fed to the diagnosis system, which can actually tell you what type of fault is there and what is the location and type of fault. So this is basic structure for model-based fault diagnosis. Here we can have the same model-based fault diagnosis being applied using neural network-based fault detection scheme. Here we can train different neural networks for different types of faults. When the signal is applied to the motor, the same current or vibration signal is measured from the motor's terminals, and also fed to the same signal is fed to the model. And there are some residuals being generated by subtracting the two signals. These residuals or the differences are then fed to the classifier for decision making. Okay, so this is the general approach for model-based fault diagnosis. Okay. So there are various other methods like fuzzy logic, wavelet, continuous wavelet, STFT. Other methods can also be used for feature extraction and classification. Okay. That's all from my side. Now I will show you some video regarding the data acquisition and how to analyze the data which is being acquired. So this is basically induction motor which is running, and we are acquiring the vibration data using this accelerometer, and the current. Okay, current and voltage signal is also acquired using the DAC hardware, data acquisition hardware from NI, and this is the signal is fed through this LAN cable to the computer, where the signal is further analyzed using National Instruments LabVIEW program. So this is the block diagram of the system, and this is the front panel. We can have the data being acquired here, and we can further analyze the data for the fault diagnosis. Okay, this data can be saved for further analysis also. We can save the data. Just like this. We can save some data, and then we can further analyze the data using LabVIEW. This is the acquired data. There are various files here. We have a TDMS file extension for the data acquired from LabVIEW. Okay. So this is basically the data acquired by ABB, which the ABB has shared with us. These are the various parameters of the motor which is analyzed. So these are also recorded at the time of acquisition. And this type of report is being generated by the system software. This is an automatically generated report by the software. So here various parameters or report summary is also given here. So these are the table of contents of the report. This is the procedure for acquisition of data. These are the points where the accelerometers are placed, and this is how the current or voltage are measured. These are the various parameters being calculated by the software, like harmonic components, voltage unbalance. Okay. So this data can be analyzed using this software tool. This is being developed in LabVIEW. We have to just select the folder in which the data is stored. Okay. Then we have to select the type of analysis, motor current signature analysis, and then time domain analysis or frequency domain analysis can be done, can be selected here. So when we select the type of analysis like time domain signal analysis, we can see the actual waveforms which are acquired from the motor terminals. This is the voltage waveform of motor. We can perform frequency spectrum also, frequency domain analysis. Okay. So we can select various windows for FFT. This software can process the acquired signal, and it will generate the frequency domain spectrum. Here you can see that fundamental 50 Hertz frequency is there, and also there are some sidebands. You can actually measure the magnitude of these sidebands and can analyze the fault's severity. So we have various tools for measuring the magnitude and frequency component in the signals spectrum. Okay, so this is how we can analyze the data in the LabVIEW. So any questions?